All right, let's move on to another very important topic is what is going to happen when that wave is going to travel from the antenna to your laptop. And actually a lot of things can happen. And keep in mind that this is still in the scope of the CCNA exam, trying to have you understand the physical characteristics of the waves. Some of these characteristics are perfectly relevant indoor, where we work most of the time. Some of them are more relevant for the outdoor environment. But regardless, you have to understand them all and be able to describe them all. So one first item we want to look at is absorption. So welcome again to my backyard. Here you see some light, the light from the sun actually going through that lens. And I just wanted to be able to have a focus point to show you the example with light. And see if I put something in between, something rather transparent, you see the light behind is absorbed. You don't see as much, it's not as clear as it was before. Okay, there's also the color, etc., but that's not what is important. What is important is that this object takes some of the light, and that makes there is less light below on the ground. If I take something thinner, like this glass, for example, you don't see this effect so much. So the absorption here is going to be less with this glass than it was with the thicker bottle. So the same happens for Wi-Fi. When you have a wave traveling from your antenna, it's going to be hitting objects. Light, you know how it behaves. If it hits a wall, it's not going to go through it. But absorption depends very much on the type of frequency you're working with. So Wi-Fi may partly or not go through walls, and it may be absorbed by other obstacles that would not stop light. So what happens? When that wave hits that wall, the energy of the wave is absorbed by the material of the wall. If it's entirely absorbed inside the wall, well, there is no wave going outside on the other side. But if the wall is thin enough, then you may still have some energy left on the other side. This is pretty much what happened with my red bottle. It was absorbing part of the light, but not all of it. And that's why you could still see some light, well, red of course, but you could still see some of it behind on the other side. So for Wi-Fi it's the same. If it goes through an obstacle and that obstacle doesn't take all of the energy, then you have some of the energy left on the other side, and that transcribes in simply the amplitude being lower, smaller. You see my wave between the two walls is just smaller. It's a way to show that there is less energy in that wave. The frequency and the wavelength did not change, right? Nothing is affecting that frequency and that wavelength. And this is where my example with the bottle is different, because the bottle has a color, so it's going to change the color of my lights. But in Wi-Fi and wall, this doesn't happen. The wave just goes through, same frequency and of course same wavelength, just less amplitude. And if you keep adding obstacles like you have on the second wall on the right, then it may take so much energy that there is nothing left and the wave stops. So absorption, of course, is a problem we face with Wi-Fi all the time. Every time you send Wi-Fi around, it's going to go a certain distance, it's going to go through some obstacles, and those obstacles are going to take some of that energy. The question is, what obstacles and what energy are you going to be talking about? In some cases, you want that absorption so that you limit the size of your cell. In some other cases, you want to cover an area and you have to budget the absorption to know if your wave will be strong enough to reach that point.